Today we're going to talk about something that you might have heard before. It's the term isotope. So what in the world are isotopes? Well, we know what atoms are, right? Atoms are the fundamental building blocks of everything around us. It's the stuff that makes up the world around us, that makes up us. Now, isotopes are a little bit different because isotopes are atoms of the same element, but they actually have a different number of neutrons. So the number of neutrons changes, which means that we'll actually see a different mass for each isotope. Now, why does that matter? Well, that's a good question. If you will, that you walk into a candy store, and as you're looking at the shelves, you see Sour Patch Kids and gumdrops and gummy bears and Skittles and M&Ms and all kinds of different candy, and it's very easy for you to tell, even with your eyes closed, the difference between a Sour Patch Kid and I don't know, a chocolate bonbon, right? Very, very different things. Just the same way that we can easily tell the difference between an atom of oxygen and an atom of sodium, let's say, because they behave differently. So it's very easy to tell the difference there. But let's say that you walk out of the store with a bag of M&Ms, hopefully you bought them, and you open this bag up and you close your eyes in delight as you start to eat these delicious M&Ms. Now, as you eat them, you'll find that they all taste the same, right? But when you open your eyes and look at them, you notice that they all have different colors. That's a little bit like isotopes. So isotopes are, again, atoms of the same element, which means that they behave the same chemically. There's no way that you can really tell just by how they react in a chemical reaction, ordinary chemical reaction, but they do differ slightly in their mass, right? So let's take a look at an example of this. Okay, let's talk about carbon. Everyone knows and loves carbon. So carbon can be written a couple of ways, but one way that we could write it is to actually write carbon-12, 6. Now this number in the bottom left-hand corner, that's the atomic number, sometimes abbreviated Z, which comes from the German Zahl, which means number, so atomic number. This is the number of protons. Okay, and remember that the number of protons is going to define what element we have, right? So if I have 6 protons, it has to be a carbon. If I have more than that or less than that, it cannot be carbon. But something that can change is this number up here in the top left. Now that is the mass number. That is sometimes abbreviated A, and this is actually the number of protons plus the number of neutrons. Okay, so if I'm looking at carbon, 12 has a mass number of 12. 6 of those, remember, 6 of those are protons, which means that the remaining 6 have to be neutrons. So I know that carbon-12 has 6 protons and 6 neutrons. Now there's a different version of carbon, known as carbon-13, which looks like this. Now, again, the bottom left-hand number tells us it has 6 protons, otherwise it wouldn't be carbon. Now this number up here is again, the number of protons plus neutrons, so 13 minus 6 means that we actually have 7 neutrons this time. Okay? And there's also another version of carbon, carbon-14. This one happens to be radioactive. This is the carbon that you hear about in the news when they talk about carbon dating, not Match.com dating, but this idea of figuring out how old something is based on the amount of radioactive carbon that's left in it, the ratio. So here we have 6 protons, right? How many neutrons? Well, 14 minus 6 is 8, so we must have 8 neutrons. All right, perfect. So that's the first thing that we need to understand about isotopes, is how to figure out the number of protons and neutrons that we have. Now another thing that you might be a little bit curious about is if you look at the periodic table, you probably all have this on your wall or your shower curtain because you love it that much, right? So take a quick look at carbon. The little box would look something like this. Okay. Now the number up here at the top, okay, that's again the atomic number, Z, the number of protons. So this tells us that carbon has 6 protons, which we know. We have the letter, or the symbol, telling us that this is carbon, but we also have this right here, 12.01, and this is the atomic mass, or the atomic weight. Now, you might be thinking to yourself, why in the world does it say 12.01? That doesn't make a lot of sense. I just mentioned that there's carbon-12, carbon-13, and carbon-14, right? And so it turns out that the atomic weight isn't just one isotope. This is actually a weighted average of all the different isotopes. So this is taking the carbon-12, the carbon-13, and carbon-14, and looking at all of those and taking the average, a weighted average. This is another way of writing those isotopes, carbon-12, 13, and 14. Now, remember that this is a weighted average. This is a bit different than a normal average, because you might say, well, you know what? If I wanted to take an average of these three things here, 12 plus 13 plus 14 divided by 3, oh, that comes out to 13. So the average is 13. So why doesn't this say 13? Well, because we're not taking just a typical average. We're actually taking a weighted average, right? Let me give you an example of this, right? Let's say you go out inside in your yard and you find some clovers, right? And how many leaves are on a typical clover? Well, 3, right? So that makes sense. Have you ever seen a 4-leaf clover? Right? People are always looking for these because they bring you good luck, right? That's a horrible looking clover, but anyway, let's say that you walk out there and you find a 4-leaf clover. Okay? And it turns out that some of these are, some clovers are 4-leaf clovers. In fact, there are actually scientists that study how frequently 4-leaf clovers pop up, and it's something crazy like if you had a square meter of clovers, you'd actually find 2 of these bad boys somewhere buried within that. So they're rare, but not, insanely rare. Have you ever seen a 5-leaf clover? Okay, I found one in my life. I was actually about 10 years old, getting into the car, and as I look down, I suddenly see this 5-leaf clover. It's like the genetic X-Men of clovers. And I pick it up, and I yell to my dad, "Hey Dad, if a 4-leaf clover gives you good luck, what does a 5-leaf clover give you?" And he turned to me and he said, "Cancer." So I dropped it, and I wish I had kept it. But anyway, so it turns out there are some 5-leaf clovers out there. Now, but they're obviously extremely rare. So if I asked you, what is the average number of leaves on a clover, what would you say? Well, you wouldn't say 3 plus 4 plus 5, add those together, right? That gives you 8 and 12, divide that by 3. Oh, the average clover has 4 leaves on it. No, that doesn't make any sense, because the average clover that you walk out into your yard and look at is not going to have 4 leaves. Instead, we need to take a weighted average. So what we need to do is we would actually look at the abundance of 3-leaf clovers, the abundance of 4-leaf clovers, and the abundance of 5-leaf clovers, and we should take all of those into consideration. Now, when we do that, you might find out that the average number of leaves on a clover is something like 3.01, right? Because most of it is in the form of 3-leaf clovers. Same thing happens with carbon. When we're looking at carbon, the vast majority, maybe 98% of all the carbon that we know of, is in the form of carbon-12, right? There's a tiny little bit of carbon-13, and then a super tiny amount of carbon-14. So when we do a weighted average of the 3, it actually comes out to about 12.01. Okay. We could actually try this in a quick problem. So let's say that we have 2 isotopes of chlorine, which is true. There's chlorine-35 and there's chlorine-37. Okay? And the mass of chlorine-35 is 34.97, and the mass of chlorine-37 is 36.97. And it turns out that the abundance of this is 75.78% chlorine-35. I'm actually going to turn that into a decimal, though. So 0.7578. Okay. The abundance of chlorine-37 is 24%, right? We're going to call this 0.2422. These numbers are things that you'd have to look up. These are what scientists come up with. There's no way to just look at an isotope and say, you know what, I bet about 75% of the chlorine is in that form. But if we multiply these together, we're going to get 26.50, and here we're going to get 8.95. And when we add those two numbers together, we get 35.45. And so this is a weighted average of the atomic weight of chlorine. If you happen to look at your periodic table, I bet that's what you'd find. All right. Thanks for joining me as we talked about isotopes.